4.5, which is going to be approximating 1. So we've seen that we can, in theory, implement any unitary operator on our Hilbert space just with a single qubit operator and C0. So now, if I remember rightly, we calculated an estimation, and that was of order n squared 4 to the n, so it's not very efficient. Single qubit and C0 gates to implement our arbitrary unitary operator on our 2 to the n dimensional space. So what we want to do today, the problem is that our single unitary operator, well, the space itself is an infinite space. Complex is infinite. So if we start off, let's say, with our state in the state all zeros, we can't hope with a finite set of gates to end up with every single possible state, because there's an infinite number of states. So what we want to do is get near, and that will be one of the challenges today, is like how many gates do we need to be able to get near to an arbitrary state, and we cannot hope to implement every single arbitrary unitary operator on a single qubit operator either, for the same reason, because there's an infinite number. Okay, so with a discrete number of gates. So what we want to do is to approximate quantum circuits. So let's U be a unitary operator, and we want to implement and V be the unitary operator we actually implement. So we define the error. So let's define the error. How should we define the error between these two operators? Well, one obvious choice would be to say, okay, well, if we look at what the difference between U and V does, let's see what U does to any gate and V does to any state, and what V does to any state, and look at the norm of the difference of what we end up with. Then an obvious thing to look at would be maximizing over all possible states the length of the state that we end up, which is the difference between the two states we end up with. Now we can justify this definition if we consider the probability. So if we say that let PU be the probability of measurement n, which belongs to some problem, after U is performed. So what would that probability be? So this would be so we've applied U. So that's a bit, so the reason I'm using just m here, so we're thinking that m here would be m for some. Okay, so that's just the fact that that's just simplifying the measurement things by using it as by assuming that we have a problem. So that would be the probability of u. So let's calculate what's the p of u minus p of v. And we're going to see this probability is in fact bounded by this error. Okay, so that's going to be the idea. Well, clearly that's going to be I'm going to, instead of just writing down this, I'm going to write down two terms which is going to help us. I'm going to write down this negative and then positive. And then I'm going to take away this with it. And I am only just about going to have space. Okay, so all I've done here is I've subtracted and added the same term. Because now I can put this together, and this is going to be let's say.
There's something weird on the third term, right? Or like you wrote phi twice or something.
I was getting ahead of myself, thank you. And I'm missing a V here as well. Ah. Okay, that's just meant to be the probability of V there. So if I now group together this U minus V and this V minus, U dagger minus V dagger, this is that MV. Okay, so that's just now grouping together these two terms and these two terms. And what I want to do now is use the triangle inequality to say, let's go to that one. And this is now less than this one. So I should say where for some reason that should be yes. This is now plus, right? Because this is U dagger minus V dagger. Okay, so let me change this again. Sorry, let me call this U minus V of the psi, and then I can get rid of some psi, so I can simplify this because this is then just different state here, and here, and here, and here. Okay, so now all I really want to do is get this in terms of the norm of delta. Okay, so now we can use Cauchy-Schwarz on each one of these two terms. The cleaner has left me some tissues, I see. I left the computation of the 14 gates at the top of the blackboard. So to gain some, I must have gained some sympathy, but left with some tissues. So now Now let's have a look at one of these. We can bound this. Basically, we're going to bound this by the norm of delta. So let's have a look at this. So note by Cauchy-Schwarz. There's a W missing here. This norm here that should be less than the square root of this norm with itself okay, and what we have here then is this is some phi m dagger phi, and this is norm of delta. And the reason I've written this, so that I can take this is now, I'm taking this u in here with the psi to give me a different state u psi. I then substitute in the m with the n. One of the mm's goes into there to give me phi. And now this is some probability. So this is less than or equal to 1. This is the probability I measure m if I'm in the state psi. So this is less than or equal to the norm of this, which is less than or equal to this, because this is the maximum of the norms for all possible states. So coming back down here, this is less than or equal to twice the error, which kind of justifies very well this definition of this being the error between two linear operators u and v. Okay, is that okay? So it's a little bit. I mean, you just got to show this as some probability. Let's say it's less than or equal to 1, and then. So I think so. It's quite a natural definition anyway. You can kind of see that it should be it, and it has another nice property. So now suppose we approximate a sequence of gates. So we have a sequence. So suppose we approximate a sequence of gates U1 Vm with V1 to Vm. So let's think about the case of 2 at the moment. So what would be the error between U1, U2 and V1, V2? Well, that's equal to the norm of U1, U2, V1, V2 psi, or some psi. And now we do the same trick again. It's the same trick. Having a term and subtracting a term. And again, we get we're going to have that this is less than or equal to the errors in both cases, because in the first term, here, obviously this is less than the error because this is just another valid state. So this is less than the error U1, V1. And here, this is less than the error of U2, V2, because we're just applying a unitary gate to this thing which was already of less than length. The maximum length of this is the error between U2 and V2. Okay, so that's just using the fact that, of course, these are all unitary. So these, I should have said, there's a sequence of unitary. Okay, so this is just some arbitrary other unitary gate, U2 psi, so that's going to be less than the error between U1 and V1, and here, this was already length at most the error, and I've applied a unitary transformation. So, and in general, and so we have the error between U1, UM, and V1, Vm is less than or equal to the sum of the errors, which we shall use almost very, very soon. Okay? So what we're going to do today is, firstly, try and prove that we can approximate any single qubit operator using just Hadamard and T-gates. Okay, so that's a very, very important thing to know when you're trying to build a quantum computer. Because we now know that we can approximate any, we can do any unitary transformation just using C0 and single qubit operators. So now we're going to say, actually, these single qubit operators, we can approximate them with just a Hadamard and a T. Okay, so that's what we're going to do now. And actually, some of it is going to be just left as an exercise. It's one of the exercises. So let's say we're going to show to prove we can approximate single qubit unitary with just H T. Right. And key to this is the following lemma. Now, just firstly recall, let's just recall something. Recall that the rotations were defined in this way. So, in particular, yeah, so this n hat is a unit vector in R3. And so this just means, this meant n1 x, n2 y, n3 z, where x, y, and z are our normal Pauli matrices. Okay, and what the lemma says is the following, that we can put a combination of h and t and get an angle which will be a irrational multiple of pi. And that's the key. Okay, that's the key that makes this work. And precisely it is that if we do t, h, t, h, then we get some global phase factor. And then r, where this theta, if we take the cosine of this theta divided by 2, it is cosine of pi divided by 8 squared. Okay, and this squared is of course very important because this means that suddenly when you try and find the inverse cosine of this, it will not be a rational multiple of pi. Okay.
The n, like the n vector. Like
yeah. Okay. Yeah. Where
should be something.
Is a multiple of. Is it sine first or cosine? Cosine. Cosine.
But if it's real, it's going to be either that or minus that, right? Is it if it has to be? Oh wait, no. Like if it has to be norm 1, or is that norm 1?
No, it's not. It's not norm 1. That's why I said it's a multiple of.
Yeah. Okay. Like I was wondering, like why would he say if it's a multiple if? Okay.
Well, if you exactly want to know what it is, okay.
I mean, it's fine. It's fine. It's fine. I mean,
I think it's. We'll work it out in a minute, but I think you'll find it's. I think it's this. Okay, but it doesn't really matter. Yeah,
no.
It's just the rotation around the axis. I mean, it's unit vector. Yeah, I mean, I in fact checked to see that it really was unit, and it's just trigonometry. So I'll leave you to check that using this. Yeah, and if you check you just have to use cosine squared plus sine squared is equal to 1 a few times, a couple of times, and it drops out. Okay, so actually most of this I'm not going to do because it's exercise something, exercise 4.6. So in exercise 4.6, we'll show that t is e to the I pi divided by 8. I mean, you can almost see it. Cosine. So, and then the rotation around the z-axis. Oh, that's good. What is now our proper identity? Z, and the h is also a rotation around. Sorry, the HTH is also a rotation around the x-axis. So HTH is Okay, so that's left as an exercise, which we will do at some point later. So we're only left now to multiply these two things together, and you can see the result is already imminent. So take that most of the work. And if it's exercise, so this then implies that TH is e to the I over 4. This is where we get our cosine pi over 8 squared. I. Yeah, now we get the x, y, and z. So we get the pi minus I sine pi over 8 everywhere. X is going to be cosine pi over 8 x plus cosine pi over 8 z. And then it's zx, which is the iy, but then we've taken the I out again, so you end up with sine pi over 8 y. Okay?
Right, and what happened to like the normalization of the n? Like maybe I'm just not seeing it. What is it?
Oh. Okay, so we can continue. So this is certainly by definition cosine of this, right? And we want this to be I sine times right? So
right, and
this then must be this divided by this.
yeah, it's squared.
This is maybe sine here. Is that right?
Oh.
Yeah, now it's right. Okay?
Oh, so it's without the square on the pi 8.
Yeah, there was no square.
Okay.
So now when you calculate the norm of this vector, yeah, you get cosine sine squared, cosine squared, sine all squared, cosine, and this underneath squared, which is of course 1 minus this square, which is this 1 minus this to the 4, and it all drops out. So we check. Now this is indeed normal. Right, so that's the crucial lemma. Now, to actually prove that this theta is an irrational multiple of pi is a number theoretical thing, which is somewhere in the appendices of Nielsen and Schwann. So we're going to take that as read. But I think logically, if you have such an angle, you wouldn't expect it to be pi times something. This square being here. So here's the theorem. Okay, so we're going to try and prove now that any single qubit operator can be approximated by these two under our definition of error, which we justified before. Okay, so we will assume as a non-rational. Well, it's not a rational particle of pi. And why is that important? Well, that means that if we look at multiples of theta, let me just divide the circle quickly into 16 bits. So, looking at multiples, let's say j and k of theta modulo 2 pi, whatever n is, here we've got n is 16, so if I take 17 multiples, I'm going to find 2 of them sitting in the same little piece of pi. Okay, so here's n is 16. And if I take enough j's and k's, I'm going to find 2 of them, which is sitting in the same little bit. Okay, just by the pigeonhole principle. So there is this j and k such that modulo 2 pi j minus k sigma is less than 2 pi over n. Okay, so that's just a very obvious, and that's usually the fact that this is never going to start repeating on top of each other because it's an irrational multiple. So, so if we fix a delta, so for any delta, small delta, there is this such that okay, so we can find, we can go big enough multiples so that it's very, very small. So if we want to approximate let's say R n hat alpha, then our claim we can find some multiple such that the error between this unitary operator R n hat of alpha and this approximation R n hat of theta to the n. Okay, so remember that this is a rotation, yeah? So this just means rotate through m times the angle theta is less than some error, which for some mysterious reason I'm going to write down epsilon divided by 3. That's just an indication that at the end there will be 3 of these things here, and then using the lemma we saw before in the previous, when we sum up the approximation of u1, u2, u3 with v1, v2, v3, we are still within error epsilon. Okay. So I still have to prove this claim. Okay, this claim will now be proven in the following lemma. which is left as a kind of dastardly exercise in Yeoman Shrine, which I thought about leaving as an exercise and then decided that I couldn't leave you all the hard work, and some of it I had to do myself. So here goes. And also, it's nice then we've got a nice clean theorem. Almost there. Okay, so let me leave. I tell you what, let me leave that and let me now finish off the proof of the theorem, and then I'll prove this lemma afterwards. Okay, so maybe that's nice in that way.
Wait, if theta weren't, like if theta were a rational multiple, would this not be true as well? Because like eventually it'd loop to 0.
If it was a rational multiple, then you're saying,
yeah, that we should somehow use more than what's written here, because otherwise, like rational theta would also.
Well, not just pi divided by 4.
If you multiply that by 4, you get 2 pi, which is sort of 0. So if you j and k are both multiple.
The point being is you're doing the same little piece of pie. Not the same pie, the same little piece of cake here.
Right. So you would all want them to be greater than 0, not just less than, right?
Yeah, I mean, you would never. I mean, if you apply 1, 4, you just go around like this, wouldn't you?
Yeah, and like if they're on the same line, we wouldn't, like if they're on the same line, like.
Well, then it would just be 0.
What?
But then it would be 0.
Right. Exactly, like that we should be using that it's not just less than 2 pi divided by n, but also greater than 0.
Okay. Yeah.
Like it's like just being less than 2 pi divided by n was also done by that. Okay.
Okay. Right. So let me try and see if I can finish this proof. We're not that far away. Yeah. So I'm going to need. So we're trying to approximate everything with h and t. That we recognize. Okay. So. Now this we already saw, this can be approximated by h and t, right? So we saw that. So this can be by lemma, this can be, this is in fact, combination of h and t, okay, because th was exactly up to global factor rn of theta, so we can just stick those together. So that's got us to rn of alpha, but of course rn of alpha is not all unitary operators, it's only the ones which are rotations around this specific axis. Okay, so now we need to recall, well, I need two things now. I need firstly exercise 4.71. So in exercise 4.71 will show that h r n hat theta h is m hat theta, where m hat, not to be confused with that m down there, is some multiple of and now it's almost the same thing as n, except the sign changes. Okay, so we get almost the same thing But this is important because now we have a non-parallel vector to n hat, which we can use to break down our unitary transformation. So we showed before, so we proved a lemma way back when. That any unitary qubit, single qubit operator U is equal to up to, and I think it was e to the I alpha RZ, is it beta? How do I use beta? Just want to use the same, yeah. I think it was beta RY gamma RZ delta. Okay, so we proved that we could break down any unitary into some global factor here, and then these three rotational things. Now, if you look at that proof, the reason it worked was more because we have these three parameters, and one of the parameters is the fact that the U was unitary. You kind of lost one of your degrees of freedom. So, in the same way, one can prove, and I'm going to, in the same way, just by, if you like, changing the basis here from the axis for the y and the z-axis to the n hat and the m hat, we have that U is up to global factor Rn hat of something, Rn hat of gamma, Rn hat of delta. Okay, so that's just changing the axes in our block sphere representation from y and z to n hat and m hat. Well, of course, now this, we can apply this to each one of, to this and this, and we will have an error. So hold on, let me get myself some room. So now I can approximate each of these three because this is then Rn at beta, using the fact that this equality here, this is Rn hat, n hat. Delta, and now I can use this approximation here to approximate these angles with some multiple of theta. So this is now, so let V equal Rn hat theta to, let's say, the B, H Rn hat gamma to A, H Rn hat delta. So where we choose these, where A, B, and C are chosen so that the error between Rn of beta, for example, and Rn hat this to the B is less than epsilon divided 3, etc. Okay, so the error between this and this using what we just had down here, will be less than epsilon divided by 3. So in each one of these cases, the error we get is epsilon divided by 3, and we just show that the cumulative error, therefore, between these three is then less than or equal to epsilon. Isn't that nice? And these are all combinations of H and T. That's what we proved in the lemma before. And we have a couple more H's in there. Isn't that amazing? So the only bit I really cheated at so far, because I haven't actually proved that I can, this error is actually less than something which I can control. So to actually really truly, so that's the end of the proof of the theorem. And now I shall prove the claim as a separate lemma, which I could have done beforehand, but it's like kind of slightly less motivated. Let's do a big clean since we're nearly halfway through. Okay, so I want to prove that the error between this Rn hat of alpha and Rn hat of a very small angle more than alpha is less than the 1 minus. Okay, so I'm thinking beta is an extremely small angle, so this is very, very, very close to 1. Okay, so this is basically cosine of beta, yeah, which is extremely close to 1. Okay, so that's what we're going to. Oh, hold on. Even better. Okay, so this is what we're going to prove, and it's simply. This is also a little bit of trigonometry. So this is basically a definition of this is cosine 2i into I sine 2 times n1x. Okay. By definition. So Rn minus okay. So these are just the, so the d is going to be the difference in the cosines. And f is the difference in the sines. Okay, so let's see what happens if we calculate this. This. And the reason we're calculating this is because then we're going to get the norm of, we can use it to calculate the norm of this times a psi. Okay, so we're just going to have the dagger of this, which is d1 plus if n1 x plus n2 y. Oops. And dz times this. And this simplifies very nicely. Obviously, the complex parts goes, and here I have f squared. And then we already did this exercise before when we multiply this out, we just get the identity matrix here, right? Is that easy? So this is n1 squared and then the cross terms all cancel each other out because xy is equal to minus yx. Okay, so Pauli is always anti-commute. So therefore, when we calculate the norm of maybe I could skip over this, but anyway. So this would be the norm of this vector squared. We see that it follows that the norm of this is equal to the square root of d squared plus f squared. So therefore, since this is the maximum of the difference between these two, we have that. So we just need to put d and f now. So this implies that e of Rn hat alpha Rn hat alpha plus beta is now less than the square root of d squared plus f squared. And now simply application of trigonometry. What is d squared plus f squared? Well, you're going to have sine squared plus cosine squared. So this is 1. Here you're going to get another cosine squared plus f sine squared. So that's another 1. And now we have the two cross terms. So minus twice cos. Oh! I haven't got enough space for this. Minus twice sine sine. And now, because you're all, well, some of you would have been Olympiads and goodness knows what, and would have gone, oh yeah, this is. I honestly, well, I don't remember, but like I certainly didn't know what these were without looking when I was younger. But reliably told by Wikipedia that cos plus sine is cosine of the difference. Okay, so this is cosine of the difference, which is beta by 2.
Okay, like the division doesn't, like, why do we have the beta halves and the... Okay, yeah. like shouldn't we have alpha halves, or like one of them is halved and the other is not? Like there's something, right? And
Oh, yeah, no, half here, sorry. Yeah, I'm going to get ahead of myself. Yeah, and now you can check that 1 minus e to the I beta is 1 minus cosine beta.
no, there's a half in both. Like how I wrote down the definition of the D and the F. We had halves everywhere.
Oh, there are halves everywhere. Yeah, sorry, there are halves everywhere. You're right. So there's a half. Yeah. So, oh, I see. No, I think it's okay. I think it should be there. Yeah, because now, let's just see what happens. So, is the square root of 1 minus cosine square cosine 2 squared. Yeah, that's right. It's going to work. So that's square root of 2 minus 2 cosine. I think the reason they change it from this to this is only because it's more evident then that this is something very clear to 0. I mean, well, it's evident here as well. I don't know. Anyway, it's the same thing. Okay? So what it meant for us was when we did our arbitrary multiple of pi, we could then, of theta, sorry, arbitrary multiple of theta to approximate to this alpha. This means that we could choose this to be as small as we like. Okay? So this F, that's what we need. Okay, so we've successfully managed to get through and prove now. Let's take a step back. What have we proved? We proved that every unitary operator is possible to implement using only C0 and single qubit operators. And now single qubit operators, we can approximate to, let's say, arbitrary accuracy using just Hadamard and T. Putting all that together, if you can make a quantum computer which can do a C0, a Hadamard, and a T, up to arbitrary accuracy, you can implement any unitary. Okay. The question is, can this be done in a feasible way? How many of these gates do you need? Okay. So now for the bad news. So let's get rid of this. I mean, we already saw that there were something like exponential, polynomial times exponential. Things cropping up. Yeah. So that, yeah, so the number of gates we needed. Right. So let's try and answer the following question. How many gates do we need? an arbitrary state. Let's say up to distance epsilon, starting from zeros. Well, let's assume something about our gates. So let's assume that each gate has a constant number of inputs, assuming each gate so not necessarily single unitary, but definitely not some function of n, just some constant number. And that we have, let's say this is C. 2 apparently, and we have C1 types of gate. So that means we can choose N, choose C2, the C1. Trying to see where the C1 comes from. I mean, obviously we have like N, we have to choose which input from which qubit. So we should be back order N to the C1, C2 for each gate possibilities, giving in total. Adrian, what do you think?
Or what?
I'm trying to work out how many different states I can get to from assuming that I have C1 different types of gates, which is constant. Each gate has a constant number C2 of inputs. I claim that I can get to at most some n over C1, C2 to the n.
The m is what?
Yeah. If we have m gates.
Ah, right.
I think maybe they are. Yeah, each gate has these number of inputs, but then I've got the C1 gates for each one of those. Okay, so therefore I have to go up C1 choices each time. Okay, and then since I've got m of them, I've got m choice. I've got each of that m times for the m different gates, and I end up with n to the C1, C2, m. Okay, so now, so this was actually like the preamble, which was meant to be the easy bit. And now I'm going to get to the hard bit, which is to say, okay, so I can get to this kind of number of states, but I need to be able to get to all states. So what I want to do is try and count how many states there are, and then how many states within a distance epsilon of a fixed state, divide the two to find out how many states I need to be able to get within epsilon of every state. Okay, so this is quite a nice exercise. So here we go. So this we will come back to at the end, right? So now we just got to remember that we're going to get to some constant times n in total. So we can get to, we can produce at most big O of n to the Cm states under this hypothesis that we start from a fixed state 0, 0, 0, that each gate has a constant number of inputs, and we have n gates and C1 types of gates.
We know they're different, but we don't know how different they are. Like if they were all like super similar, right? Like we don't know if the states are like all like evenly distributed in like some sort of sphere, or if they're
it could be disastrous, but this is an upper bound, right?
Oh, okay, yeah.
So what we're going to just show now is that we need an awful lot even to just get within distance epsilon of every state. So so each state, so suppose, so each so what is this? This is a C2 tensor n, can be written as each, well, let's say unit. Let's just write it, let's do it in coordinate notation. Okay, so we can write any vector in this complex vector space as a vector in R2 to the n plus I times another vector in R2 to the n. And the fact that this is a unit vector, that it represents a state in our quantum system, the fact that this is equal to 1 implies that x1 squared plus x to the 2n squared plus so this is just a point on the unit sphere in R2 to the this is unit sphere. r of 2 to the n plus 1. Now, if we think about the sphere as a sphere in R3, and you got to this point here, all the things that are at distance epsilon is a little circle, well, approximates to a little circle here with this as a big radius epsilon. So you manage to get to this state, then the ones that are at distance epsilon from here are sitting on a kind of circle, approximately a circle in here. So if this is R3, this would be like the volume in R2. Yeah, here. So we go from, so surface area in R3 approximated, or covered with volume circles, circles in R2. Okay, so here, what we want, we've got a point on our unit sphere in this space, and we want to approximate them with the volume things in the volume in one space further down. So for that, we need to know formulas for the surface area of the unit sphere in RK, and then the formula for the volume as well, but then we need to use the volume from one dimension less. Okay, so let me think. So that was somewhere here. I wrote down the formula. Where's it gone? Here. Okay. So the sphere radius r in RK has surface area, and the formula is, I'm going to do k plus 1 just because it's slightly, has this formula. And you get the volume and volume you simply integrate that. And this is the gamma function, classical gamma function. All we need to know is that you can prove by parts, if you do integration by parts, that pi of n is n factorial. I mean, it's always simply, this of course is nonsense. This should be integrating with respect to x, and this should be z. And which makes all of this complete nonsense again. So hold on. Adrian, look up the formula of the gamma functions. I thought I did it by heart earlier and I got it all completely wrong. is this? Yeah.
X z minus 1, and then e to the minus x.
That's z minus 1 here.
The Wikipedia one does. Oh, right. Okay, no, but they shifted it. Yeah, so they have gamma n equals n minus 1 factorial.
Yeah.
So yeah. So if you have the thing on the right, then yeah, it's just the z.
Okay, so gamma of n is n factorial, and gamma of n plus a half, which are the only two things we care about, is somewhere it's written down, is 2n factorial divided by 4 to the n factorial minus square root of pi. Okay, so they're the two things that we need to know, because from this we can now discover exactly how many things we need. So we need to cover in our units, on our unit sphere, so the surface area we need to cover the surface of unit sphere in R to the. So this has got 2 to the n plus 1. Coordinates with volumes with spheres or radius epsilon of R to the 2 to the n plus 1 minus 1. Okay, so it's just, as in this picture here, if you were covering R3 with the ones with little circles in R2. So it will be, therefore, how many do we need? We need to put R is 1 in this formula and divide by R is epsilon in this formula, but with K 1 dimension less. So this will be, so we need at least so this K here will be 2 to the n plus 1 minus 1. So that's pi to the, this is, it's going to be 2 to the n plus 1 minus 1. So we're going to add 1, so that's simply pi to the 2 to the n. R is 1 divided by pi of 2 to the n. And we're going to divide that by this thing, 2 pi 2 to the n minus a half, epsilon to the 2. So here now we've got, this will be k is 2 to the n plus 1 minus 2. So this is 2 to the n plus 1 minus 1. That's divided by 2 to the n plus 1 minus 1 times pi 2 to the n minus a half.
Wait, why did we subtract the 1? No.
Because I've used the formulas for R in R to the k plus 1.
Ah, wait, what?
So, which looking back was a bad idea, because I copied them from somewhere.
Oh, right.
Yeah, so I probably should have done that. Anyway, this all simplifies down to, square root of pi. This 2 to the n plus 1 minus 1 comes on top. This is below, this epsilon 2 to the n plus 1 minus 1. And here I have, this comes on top, this is upper gamma is still below. And this is big omega of 1 over epsilon to the 2 to the n minus 1, since, and this is just something you can check, that this gamma 2 to the n minus a half times 2 to the n is bigger than gamma of 2 to the n. Okay, that's just some, you can check with some property of the gamma function, which we can check from these formulas here, if you'd like to. So this big omega is the opposite of the big O. Okay, so the big O, I'm not sure I mentioned that before. So if F is big O of G, then G, well, if and only if, G is big omega of F. Okay, so it's just like, is this giving us a lower bound? So now we only have to recall what we had before. Yeah, so the rest of these 2's doesn't matter. I mean, this 2 here doesn't matter, this root pi doesn't matter. So we can just use this bit to knock out all the exponentials, and we just get left with the epsilon being the important term here. So now we recall, which I was meant to not erase, but I did erase, that we needed, that we can reach at most. We saw that we could reach at most big O of n to the c n. So we need n to be at least let's say, not quite very much bigger than, let's say, let's put a constant in here. Let's put a constant. So this gives us C m log n bigger than log of 1 over epsilon 2 to the, and then the log bit comes down, so let's say that's then 2 to the n logarithm epsilon, 1 over epsilon. So n is bigger than some constant times 2 to the n over log n.
Why 2 to the n, and what happened to the 2 to the n plus 1 minus 1?
Can't I just multiply it by? Well, it's just multiplying by 2, isn't it? It's got chucked into the constant. Yeah, if I just take this out, this is bigger than 2 to the n.
Okay, sure, fine. Okay.
I'm just trying to simplify things just to see what's the important bit. The important bit is its exponential divided by logarithm. Now there's a theorem. So not good, yeah. I mean, not good in the sense that you need a lot. So corollary. So there exist states which require at least some constant 2 to the n logarithm gates to be within a distance. Okay, so just to emphasize, so what we proved is there exist states somewhere in a Hilbert space which require at least this many gates just to get within the distance epsilon. So that's kind of the bad news. Yeah. Now there's a theorem of Sola. The Solovay-Pipé theorem states that we can approximate n gates with big O of m log log m over epsilon to the c gates. These would be the Hadamard and T gates. Okay, so we can do our approximation of n gates with this many of gates. So we saw that an arbitrary. So we saw arbitrary quantum. Arbitrary unitary operation. We had n was roughly n squared 4 to the n. Yeah, so that's what we proved when we decomposed our arbitrary unitary operator into two-level unitary operators and then into C-naughts and single unitary operators. So now we're saying that if we approximate n gates, i.e. this would be n squared 4 to the n, then we'll need this many to do our approximation, which if we compare here is actually not so far off, right? So there's a polynomial thing here, the exponential log kind of.
Wait, like what do we mean with we can approximate m gates with m log c into the epsilon gates? Like isn't the thing on the right going to be bigger or?
Well, I'm assuming this is our approximation with h and t.
Oh, okay. Right, yeah. Right. So any m unitary gates with this many h and t gates? Like it's m arbitrary gates with the,
I think this should be single cubic.
Okay, yeah.
So approximate m single cubic gates, which was the approximation we were doing before, yeah? That's the one I'm talking about. Gosh, time flies when you're having fun because I've still got quite a lot. 20 minutes. Okay, well, I'm going to push on. maybe I will need a little bit on Thursday just to finish what I want to say, and then we'll do the exercise. I think we'll probably have time to do the exercise. So we generally have a little bit of time to spare. And if we don't finish them all, then it doesn't matter. Then we will just have them up into the drive for to look at over Easter. So the last little thing we're going to do in this chapter is just to talk a little bit about what we saw in the introduction, which was quantum computational complexity. And there we introduced some different computational classes. The BQP was decision problems that can be solved with bounded probability on a quantum circuit of polynomial size. We were decided that the best thing to compare this with on the classical side was decision problems that can be solved with bounded probability on a classical circuit polynomial size. And then we saw that P space was decision problems which can be solved using positive polynomial space but maybe with no time limit. And we saw that these polynomial space would allow us to solve MP problems by simply going through all the witnesses and checking to see if they're a solution. So what we want to show now is that this complexity class is contained in here. So we saw that since we can simulate any classical circuit on a quantum circuit, that BQP must be contained in BQP. And now I want to show that BQP is contained in P space. And I'll give like a sketch proof of this. You can be far more readers. So let's suppose we have n qubit quantum circuit. And we do a computation where this P of n is polynomial in n. So without loss of generality, we can assume that we start in 0, 0, 0. Assume we start in 0, 0, 0 and apply U1 up to U here. Okay, so there are unitary gates. And that we measure, so we will end up, and measure, so at the end we measure I with probability so this 0 is now representing this line of n zeros, okay? Do I want to write 0, 0, 0? Okay, so if we can solve it on our quantum circuit, that means that we've started in 0, 0, 0, we've applied some gates, and then we've done a measurement, and we're going to measure this probability phi, and it's going to tell us something about our decision problem and allow us to solve our decision problem. So to be able to say, okay, if we can do that, if we can tell you how to calculate this probability on a classical circuit, but with polynomial space, then we can do the same thing. Then this problem lies in P space. Okay, so we have to show, to prove the theorem, we have to explain how to calculate this probability on a classical circuit using polynomial space. Okay, so we're only allowed to use polynomial space, but it doesn't matter. We're no longer concerned with how many calculations we have to do. Well, the idea behind this then is we use an orthonormal basis and recall that if we sum over our elements in our basis, then we get the identity. And the simple idea is that we can calculate this by inserting in here the identity. So this, I'm just going to write 0 for the long zeros now. So for each one of these identities in here, which I inserted between my unitaries, I'm going to write this. And now bringing the sums out, this is now let's give this a label. Let's say this is x pn minus 1. So this could be x1, because we don't. Also, I thought we need 1 here. And let's say this is x pn minus 1. Then this will be the sum over I in 1 to pn minus 1 of xi in B of phi upn x pn minus 1. That should be here as well. X pn minus 1 u pn minus 1 x1 x1 u1. Now, forgetting how many terms we've got, each term here has just got a polynomial number of complex numbers which we have to multiply together. So we can tell our computer, so my computer sitting here, how to multiply together these p to the n complex numbers. And then for each term, just keep track of this sum. So each term can be calculated in polynomial space. And we can then sum up, we can keep track of the sum. And even though there are, how many terms we have here? B has size 2 to the n, so this is 2 to the n p n terms. We can add them all up in polynomial space. Okay, so that's kind of like that's the kind of idea behind it. It's more of a sketch proof than a totally rigorous computer science type proof. so the idea is then that actually, yeah, so if we can solve this with polynomial number of gates on a quantum computer, then we can solve it on a classical computer with polynomial space with no time limit. Simply just by going through each one of these terms and multiplying together these polynomial number of complex numbers, adding them all up, term by term, keeping track of the sum, and eventually we can calculate the probability that we had to calculate, which will be then the norm of this complex number. So then we have that.
Wait, so are we supposed to understand the sum? It's like it's all over all combinations of x. Yeah, it's like I think I get what the sum is trying to do, but like with the sum notation.
Yeah, I couldn't work out a nice way of writing this down. So we basically got p to the n, p of n bases b.
Yeah.
Right? And so for each basis here, you choose which element from the basis you put here.
Right.
In the first, second, up to the last one. Actually, maybe it's p to the n minus 1. Yeah, it should have been p to the n minus 1. Yeah.
But then the sum is from I going from 1 to Pn minus 1, and then for all the x, I, and b.
Yeah, I mean, maybe you should do bi's being exact copies of b, yeah?
Yeah, but like there's no i's in the sum, like in the term to the right, so like it's hard for me to relate the sum notation and then what we're actually adding up here. It's like we choose all possible permutations or like all possible choices of or something, but
yeah, how do you mean? Yeah, it's every single possibility. That's so these are the x. Oh, I see. Oh, I see. There's no x's, are there? Okay, gotcha. Problem. Right. So how do we write this down? So this should be then. So if I put x to the pn is equal to phi, this is the product of xi plus 1 uixi times x1 u1 0. Is that better?
oh, okay. But then we have the I there twice, or
Sorry?
like the I is there twice. Like we have an I in the first sum, and then
Yeah, because you end up with xi's, xi's, which is coming from the identities things.
yeah, but like I don't understand how like the sum notation that we've written is really like the sum of all sort of possibilities between the x's and the. Like, is that really what this sum notation would say we're doing?
Yeah, I mean, simply you've got every single time where you substituted in this, the identity, this has to run through all.
Yeah, all every and everything. Okay. Okay.
Who knows? Horrible. So I will think about that some more, try and work in a better way. So we have this inclusion, which is interesting because we don't know if this is different from this. So if we could just prove that this is different from this, we would actually prove a direct, strict inclusion between two classical complexity classes. Okay, so that's what makes this theorem very interesting. I've run out of time. I think we'll skip straight to the exercises on Thursday. Okay. So let me stop this.